Okay, I have the honor of introducing Jun He for his second talk on Lorentzian polynomials.
Okay, thank you. Let me remind you what happened last time. So I told you some basic of the theory of Lorentzian polynomials. And central to the whole story was the notion of convexity for subsets of lattice. So this is the notion of M convexity. And I have defined something that we call M convex sets, subsets of n to the n. So this notion has many different names. So people living near Tokyo calls it M convex sets. People living in Boston area calls generalized permutohedra, or integer points of generalized permutohedra. But the property in question is
Some people call it polymatroids.
Yes, there are many different types of people. So, yeah. So the property is that whenever you have 2 points in your convex set, alpha and beta, and what you want is that given the directions EI and EJ, the standard directions, you want your convex set to contain these 2 new points, which is alpha minus EI plus EJ and beta minus EJ plus EI. And to be truly honest, you should not forget about these quantifiers, and they exist. So this is the property. You don't want any holes in this particular way. So in particular, this condition forces the convex rule of an M-convex set. All the edge directions must be in the root direction EI minus EJ. So when you get bored while listening to this lecture, you may start wondering what might be the corresponding analytic theory in other types, if you're that kind of person. So at least in this case, the starting point was the many different descriptions of this set LDN of the space of Lorentzian polynomials of degree d in n variables. This is my notation for Lorentzians. Of degree d in n variables. And you can describe it in many different ways. So for example, you could say that it is the closure of the space of homogeneous forms with positive coefficients. And all the quadratic forms that you can get by taking repeated partial derivatives have the Lorentzian signature. So that was one description or definition, if you want, of Lorentzian polynomials. And I told you that this set is, in fact, can be also characterized as the space of homogeneous forms with non-negative coefficients with M convex support and all the quadratic forms you can get from your original homogeneous polynomial have at most one positive eigenvalue. No, I and j are just 2 different coordinate directions.
Why
So given any alpha and beta in a given M convex set, and for any I with a property that alpha I is larger than beta I, that's why I've drawn alpha farther to the right, there should exist J so that beta J is larger than alpha J, so that so that was one of the first theorems. And this set also turns out to be the same as the set of strongly log concave polynomials of given degree and number of variables. Let me remind you that strong log concavity means that the polynomial itself should be log concave on the positive orthant, and all of its partial derivatives should also be log concave on positive orthant. And that is equivalent to this and that. So I have drawn a picture like this. The picture of LDN, maybe in the projective space. So first of all, this is a closed set because it's a closure of something, which is not obvious from other definition. And on the boundary, you see many different types of supports of your polynomials. And you've seen that all M convex sets appear on the boundary. For given D and N. I've told you some famous members or classes, subclasses of this Lorentzian polynomials. One of the most well-studied class is the class of stable polynomials. The multivariate generalization of real-rooted polynomials. And this other part is Minkowski's volume polynomials for convex bodies, and they are all Lorentzian. And the Lorentzian property of Minkowski volume polynomial is like the whole point of the so-called Broom-Minkowski theory. And I also posed the problem that volume polynomials that you get from projective varieties, which is provably Lorentzian by the Hodge theory of projective varieties. And I ask how large is this set in this map? I mean, for what we know, it can be everything once you take the closure. It's just very hard to show that something cannot be realized in that way. Of course, on the boundary, there are many interesting combinatorial creatures. So here, somewhere in the intersection of the two, you see graphs. Or more precisely, there are spanning tree generating polynomials, where you sum over all the spanning trees of whatever your graph may be. On these more remote side, you see more interesting or exotic configurations. And they are basis generating polynomials. They are all Lorentzian. I also told you some naive looking properties, analytic properties of Lorentzian polynomials. For example, if you have a Lorentzian polynomial of degree D1 and maybe of degree D2. And I have told you that their product is also Lorentzian, which is completely almost obvious from this description, but very hard from that description. I also briefly mentioned in passing that another naive-looking proposition that if you have a Lorentzian polynomial of degree D, maybe in n1 variables, And then maybe you take the coordinate change by using some matrix A so that you get the same degree homogeneous form, maybe in different number of variables. And I told you that this implication is true whenever you pick your matrix from the one with non-negative entries, and so on. So in fact, let me add that implications like this is a special case of the more general principle that whenever you have a linear operator acting on homogeneous forms that preserves the property of stability, then it automatically preserves the property of being Lorentzian. So if you are one of those people who already mastered the yoga of dealing with stable polynomials, you don't have to invest too much to learn and play with Lorentzian polynomials. All your favorite tricks dealing with stable polynomials are probably applicable to Lorentzian polynomials too. For example, taking the square-free part of a homogeneous form preserves the Lorentzian property because they preserve the stability. So if you want to think of this M convex sets which control the boundary of the set as really a generalization of matroids, or if you really don't want to deal with those M convex sets which are not matroids or does not consist entirely of 0, 1 vectors, you can always apply this operator that takes the square-free terms. And then your Lorentzian polynomial will output a Lorentzian polynomial with only square-free terms, and the support of that Lorentzian polynomial is literally the setup basis of a matroid. So I try to sell you that proving the Lorentzian property is easy or easier than showing that, say, showing the low concavity property, for example. So let's compare the low concavity property with the Lorentzian property, or strong low concavity. So this is a nonsense because strong log concavity includes log concavity, and not only that, you also have to show that all the partials are also log concave. So you have to, in principle, do more work to show this, and not only that. But this is like our favorite paradox in mathematics. If you have some hard statement that you wish to prove and could not prove, then what do? You make the statement even harder. And then it's easy to prove it. And it implies the original hard statement. This is exactly that situation. This is our most powerful tool in proving statements. So think of some simple statement like this. Logarithm of my homogeneous polynomial, maybe it has two variables, fx, y, is concave on positive orthant. Okay? I mean, it may be true or not true, depending on what your f is. So maybe my f is this polynomial. Let me write it in normalized form. Let's make this 3. So I'm writing in this perverse way just to adhere to the principle that I'm always using the exponential generating function. And I can ask this question for this polynomial. Is it true or not? I'm sure nobody, not sure, but I hope that nobody in this room is quick enough to see the answer. I mean, at least to me, it's a completely painful statement to check. I mean, what do you have to do? You take the log, and then I want to check the concavity. So I take the Hessian, and then which will be a rational function in x and y. And then I want that to be negative definite. So I have to write down all the principal minors. And I hope that they are all negative on the positive orthant. How do we check something like that? We just pray really hard that the expression that we get is a sum of squares. Okay? You may be able to do it. I mean, it may be not true, or it's just very painful. So I chose this polynomial because for this polynomial, the statement is true. And the way I see it is to compute the determinant of the Hessian of the log of f, which luckily 3 of x squared minus 3y squared to the square over x squared y squared, x squared plus 3y squared to the square. So this is positive. But let's think of the strong log concavity property, first of all. It's clear that this is not strongly log concave, right? Because there is a hole in the middle. There is alpha is x cubed y and beta is xy cubed. And I drag each of them toward each other so that I get x squared y squared, but I don't have that term. So it's not strongly log concave. So showing that something is not strongly log concave is usually easy, but showing that something is strongly log concave is also easy. So let's compare the situation to this. So maybe I add one more term, maybe something like this. Yeah, let me keep the same numbers. And let's ask the same question whether this is log concave on the positive orthant. That's almost obvious because this is strongly log concave. How do we check the strong log concavity? We check the Lorentzian property. Lorentzian property, the M convexity of the support is clear because I just have 3 dots in the root direction, EI minus EJ. So I only have to check the signature condition and what are the quadratic forms that we see. These are just given by the coefficients 1 and 2 and 3. And I have to check 3 things. 1, 2, 2. No, sorry. So I should start from 0. 0, 1, 1, 2. 1, 2, 2, 3. And 2, 3, 3, 0. These 3 are the quadratic forms that I would get by partially differentiating this polynomial with respect to x and y. And this is one reason why I normalize in this way. And it's clear that this has Lorentzian signatures, determinant negative, determinant negative, determinant negative. Therefore, it is concave on the positive orthant. So let me try to convince you that checking Lorentzian property is really far much easier than log concavity by showing you another example. So let's say you have n vectors in some d-dimensional vector space. And let's say you have a J, which is the collection of bases of your vector space that's contained in A, that entirely consists of vectors in A, viewed as 0, 1 vectors in n to the n. So just to be really concrete, but the argument applies in the same way, let's consider the situation when A is the f2 to the 3, everything except 0. So that I'm looking at that picture that was on the board before. 1, 2, 3, 4, 5, 6, 7 vectors. And let's consider the polynomial f of a j, the generating polynomial for the basis j. So it's a sum over j, and there is a degree 3 monomial, ijk, for each one of the bases. So this is a polynomial in 7 variables, because I have 7 points or 7 vectors. And it has clearly degree 3, because any basis has 3 vectors from A. And how many terms? I have a 3 terms, except that those triples on one of the 7 lines do not appear. So 7 choose 3 minus 7, so that's 28 terms. And maybe somebody asked you whether this polynomial in 7 variables is log concave on positive orthant. I mean, that is painful to check. What do? You take log and compute the Hessian, so you get the 7 by 7 matrix with rational functions, and this time you pray really, really hard that the determinant is sum of squares or something. But it's easy to check that this is strongly log concave. So let's check that that is strongly log concave. So how do we check that? Well, first we have to check it clearly has non-negative coefficients, so we have to first check that it has M convex supports. So we are checking the symmetric exchange axiom defining M convexity for this thing, which is a famous result. And M convexity is just if you look at the Plucker relations really hard, then the M convexity becomes pretty clear. It's simply the statement that if you write 0 as sum of many numbers, then either all the numbers are 0 or at least 2 of the numbers are non-zero. So M convexity is clear to modern people. So we only have to check the condition on the quadratics, on the partials. So let's take the partial of fj with respect to one of the variables. Maybe I have a 7th point. Well, it doesn't really matter which point it is. Let's just call it 7 and take the partials. And then what is the polynomial? It is a polynomial of the same kind, basis generating polynomial of the vector configuration obtained by projecting away from your chosen 7th point. So this is f of let's write it a projected from 7. And what is a projected from 7? If I'm projecting from one of the points, the remaining 6 points looks like this, because there are 3 points on a line in the original configuration. Maybe this is my point 1, 2, 3, 4, 5, 6. And I'm looking at the basis generating polynomial for this. But that's easy, right? Because this is 6 vectors in 2-dimensional vector space. And being a basis is just checks whether the vectors are parallel or not. So this is just xy plus xz plus yz, where x is w1 plus w2, y is w3 plus w4, and z is w5 plus w6. And the question is whether this quadratic form has Lorentzian signature. We know what this matrix is. It's the 0, 0, 0, no squares. I have a 1s here. Well, that looks like a difference between the constant matrix and the identity matrix. So we know that it has eigenvalues 2 and -1 and -1, which is Lorentzian signature. I mean, and this argument is completely general. I mean, it doesn't really matter which configuration you started with in whatever dimensions. The proof always reduces to the analysis of vector configurations in dimension 2, which is trivial. And you just check matrices like this. 0, 1 matrices have the Lorentzian signature. But so I have emphasized this, the central role played by the notion of discrete convexity or discrete convex sets. But of course, there is notion of convex functions in discrete convex analysis. So let me tell you how does that interplace with the notion of Lorentzian polynomials. So think of any function from n to the n with values in real numbers or infinity. Whenever I have such a thing, I'm going to write for domain of nu for the set of points where the value of nu is finite, called the effective domain of nu. And the correct thing to do is define nu to be convex or M convex, M for matroid, if basically the same thing is true. So for every alpha and beta in the effective domain of nu, and for any I, one of the indices, where alpha I is larger than beta I, you want to have another index j in n such that alpha j is smaller than beta j. So the definition is literally the same up until this point, such that what should I do? Let me continue here. Such that nu alpha plus nu beta is larger than nu of alpha minus ei plus ej plus mu of a beta minus ej plus ei. So one thing you notice is that the effective domain of an M-convex discrete function nu is necessarily convex. Because if this is finite, that's finite. That implies that both of these quantities must be finite. And of course, the most basic example of a convex function comes from convex sets. So maybe I have a convex set. Yes?
Will it be positive real numbers or just real numbers?
Real numbers.
Can be negative.
Right. But I don't want minus infinity there. So maybe I have a M-convex set, J. And if you define a discrete function nu by saying that it's either 0 or infinity, depending on whether or not your alpha is or not in J, then this is M-convex. But of course, there are many more interesting discrete convex functions than discrete convex sets in given dimension. So for example, if you have a matrix, say A, say maybe it has a D rows and N columns. Maybe it says entries in Q. And maybe you fix a prime number. Then the function, discrete function nu, from D element subsets of n, viewed as 0, 1 vectors in n to the n, with values in R. Such that the subset I of D columns goes to the periodic valuation of the determinant of the corresponding D by D square matrix extended to the entire n to the n by adding infinity is M convex. So this is one of the examples that motivated the study of discrete convexity. So for example, when P equals 2 and my A is a matrix like 1, 0, 0, 1, 1, 1, 1, 2. So I have 4 columns. Then your function, discrete function, which is defined on the octahedron of 2-element subsets of columns, where you take the determinant of, say, 1 and 2 and take the periodic valuation. So 1, 2, that has value 0. 1, 3 has value 0. 1, 4 has value 1. And 3, 4 has value 0. And 2, 4 has value 0. And 2, 3 has value 0. This is discrete convex. So if you lift this point up to the height 1 while keeping all other points height to be 0, then it subdivides your convex set, discrete convex set, into 2 discrete convex sets. So in this case, it subdivides the octahedron into 2 pyramids, where one vertex is at 1, 4, and the other vertex is at 2, 3. So in this sense, discrete convex functions subdivides discrete convex sets into many smaller discrete convex sets. And this is maybe one reason to believe that this is the right notion of convexity to pursue in the discrete setting. So more generally, this example is what people call notion of tropical linear space, which is the same thing as some other people call valuated matroids, and which is in our language exactly the same thing as M convex functions mu whose effective domain entirely consists of 0, 1 vectors in n to the n. So M convex sets generalize matroids in the same way that M convex functions generalize valuated matroids. So tropical people likes working with valuated fields like this. So I'm going to work with this K, by which I mean field of Peugeot series. With real coefficients. Okay. So elements of this field is a series with variable t. It goes on like this, C1, t to the A2, and so on, where Ci are real numbers, and Ai is an increasing sequence of rational numbers with common denominator. Huh? Ah, yes. I want different. Yes. Oh. If you want the peace of mind, you can also add a convergence condition around the origin, or things like that. So this is called the leading coefficient. And the sign of the leading coefficients gives the structure of ordered fields to K. You compare this. You compare the leading coefficients when comparing the two series. And this A1 is called the leading exponent. And taking the leading exponent of a series is responsible for the called the tropicalization of a polynomial with coefficients in K. So one thing very nice about this field is that it's an ordered field, but not any ordered field. It's a real closed field. So it has, and the theory of real closed fields have quantifier elimination. So this K is elementarily equivalent to our familiar field of real numbers. So any reasonable statement that you can think of, like statement that this polynomial is Lorentzian, which is certainly a first order statement in the language of ordered fields, is valid over the real numbers if and only if it's valid over K. So you don't have to do much extra work to play with Lorentzian polynomials over K. For example, the statement that Lorentzian polynomial, which is by definition those polynomials which have M convex support and have this signature property, is equivalent to the strong log concavity, is clearly true over K because we already have asserted that it's true over R. So we can work with them in the same way. But once we accept them as a valid field to play with, we see that the convex functions naturally come into play. So for example, these properties are equivalent for any function nu from n to the n to all to the infinity. And the first statement is that nu is M convex. And the second statement is that there is a Lorentzian polynomial over K whose tropicalization, by which I simply mean the process of taking leading exponent from every one of the coefficients, is nu. And that property is equivalent to a statement over the real numbers that has nothing to do with K, which goes like this. So for all positive parameter Q at most 1, the generating polynomial of the M convex function, or any function, by which I mean the sum over the effective domain of nu, and you look at Q to the nu alpha with the exponential generating function W alpha to the alpha factorial, is Lorentzian. over R. So these three statements are equivalent. So M convexity of sets gives the Lorentzian property of their generating polynomials. So these are the distinguished points in the map of Lorentzian polynomial space that I have drawn. And what the M-convex functions play in this picture is that they control these distinguished families. So in this, like, let me see if I still have. So if you look at the space of Lorentzian polynomials over K, now my K has a valuation, so I can take the leading terms and tropicalize. And the second statement says that, well, maybe let's take the scare-free part. To make this thing familiar. Then the second statement says that the tropicalization of this space is the so-called Lorentzian, a much studied object in tropical geometry, which is the moduli space of d-dimensional tropical linear spaces in n-dimensional space. Just throw out all the, no, so, yeah. If I have a polynomial which look like this, I just keep this. If this is Lorentzian, that must be Lorentzian. That's the statement that I have in mind.
Oh, so you just throw away all this?
Yeah, just throw away all this, yeah. Yeah, that has a scare. And amazingly, this preserved the Lorentzian property. But I'm just doing here just to make this part more familiar. There is a corresponding tropical object when you don't have the tropical thing. So for example, and what's amazing is that, again, this has a tropical structure. In particular, it's a piecewise linear object. So for example, when d equals 2 and n equals 5, then the space is famously the cone over the Patterson graph. Living in as a fan inside the all of a all to the 10. Maybe I have some 5-dimensional linearity space. So this is the same type of the phenomenon that we have seen for M-convex sets. You start with a completely purely analytic consideration. Maybe you want to consider strongly log concave polynomials over K. That's just a purely analytic condition. But once you tropicalize, then you see a remarkably intricate combinatorial creature appearing it as its shadow. And this, for example, this thing, when d equals 2 and n may be large, is known as the space of phylogenetic trees. And it has intriguing combinatorial properties that amazes many combinatorialists. But having this sort of an intuition about discrete convex functions can help understanding some other classical polynomials. So let's see, for example, think of a connected graph. And I'm going to now talk about this Potts model partition function that is related to what Sasha talked about. So maybe you have arbitrary finite connected graph. And Potts model partition function, or Q-state Potts model partition function, is this polynomial, which I view as a polynomial in W with parameter Q, the same Q, which is by definition the sum over all the subgraphs A, viewed as subset of the H set E, with Q to the KA, and the corresponding term is the product of the variables, H variables in A, where KA is the number of connected components of the subgraph VA. So just by looking at the expression, it's unclear what kind of analytic property this polynomial has. But if you're familiar with this sort of a business, it's not too hard to guess and check that this function Ka here, the K function you're staring at, this is a convex function in the sense of discrete convex analysis. So you expect the Lorentzian behavior. The only thing you have to be a little bit careful about is that this polynomial is not homogeneous. So you have to homogenize, because I don't know whether this was a good choice, but I had set it up so that only homogeneous polynomials count as Lorentzian. So let's just homogenize. And let's make it even more general by applying our powerful proof technique. So let's, instead of just graphs, we can think of any matroid or M-convex set of 0, 1 vectors. Maybe if you're not too familiar with matroids, let's just say it's coming from a vector configuration A in F to the D of n vectors, just like as in our previous example. And let's just homogenize that expression to get Z of M with parameter Q, where I have one more variable, W0, to homogenize things, and I have n variables corresponding to n elements or n vectors, where the partition function is by definition the sum over all subsets of n, and I have a Q to the minus of the rank of the set, which is in this case the dimension of the span of the corresponding vectors in A. And I have a monomial W to the A, square-free monomial corresponding to the set A. And let's just homogenize using our extra variable W0 to degree n. And of course, the theorem is that this polynomial, ZMQ, is Lorentzian. For all choices of Q in between 0 and 1. And I would say that the proof is nearly trivial. It's almost the same as that proof you see over there. So how do you check that this is Lorentzian? Well, you have to check that it has M-convex support. But the support is trivial. It consists of all the subsets. So the support is Boolean algebra, and checking the M-convexity is trivial. So you have to check that each one of the partials are Lorentzian. That's all you need to check the quadratic condition. But if you take the partial derivative with respect to one of the elements in n, then you get the same polynomial where you replace m by m quotient I, just like projecting away from I. So by induction, you know everything. You have to be only worried about taking partial derivative with respect to W0. But then what if you take repeated partial derivative of W0, what you're looking at is eventually those sets where A has very small cardinality. In fact, yeah. So that in fact corresponds to another type of induction where you project away from the general point. So essentially, with the help of the correct induction and checking the base case where this condition is coming from, almost no work goes into the proof of statement like this. But let's think about what that says. So that thing is called the multivariate Tott polynomial by Sokal. And it is really a multivariate version of the Tott polynomial defined for graphs and matroids. And if you view it in that setting, the Q is our familiar Q, depending on who you are. So Q is that Q you use when you color the vertices of a graph using Q colors. But it is also the same Q when you're counting the number of FQ rational points of, say, some hyperplane arrangement complement corresponding to that A. So to me, Q is really a prime power, but no prime power is in between that range. But just for fun, let's just plug in what we are really saying in this case. When Q equals 1, that polynomial has nothing to do with my M. It's just a completely trivial polynomial. In fact, it factors into many things. So Q equals 1, I get something extremely boring. So it's a product of linear forms. Why is it log concave? If you take the log of a product, it's the sum of the logs, and each one of them is concave. And clearly, that's the case. So let's try to plug in Q equals 0. Well, I really cannot do that because it diverges. But I can renormalize so that it doesn't. So if I take the limit Q to the 0, in the new polynomial ZMQ, where I keep the homogenizing variable W0, and if I replace every other variable by multiplying by Q, then it does have a limit. And we can write down what the limit is. So if you substitute W by QW in that expression and let Q goes to 0, the only monomials that survive in the limit is the subsets whose cardinality is exactly equal to its rank. And these are, from the point of vector configuration, these are independent subsets. So I'm looking at the generating polynomial for independent sets. And simply I have W to the A and W0 to the n minus A. But scaling by positive number and taking the limit both preserves the Lorentzian property because of our basic properties. So this must be Lorentzian. So I can specialize even further by setting all the variables Wi other than W0 to equal to one variable, W1, for all I in n. And then we get this polynomial, k equals 0 to n, fk of a m, W1 to the k, and W0 to the n minus k, where fk counts the number of k-element independent sets, subsets. And let's rewrite this polynomial into our exponential generating form so that I have an n factorial in front of it, and I have a fk to the m divided by n choose k, and whole thing divided by k factorial and n minus k factorial, w1 to the k and w0 to the n minus k. And our conclusion is that this must be Lorentzian polynomial, because making non-negative linear change of coordinates preserves the Lorentzian property. But what does it mean to this polynomial to be Lorentzian? It means that those bunch of 2 by 2 matrices with entries in this are Lorentzian. In other words, we have what is known as Mason's conjecture for any matroid, which says that for any matroid M, if you count the number of independent sets, you should see this logarithmic concavity of the enumeration. For any M on n elements. And of course, this inequality is tight, because if you take your original vector configuration to be generic, then the number of k-element independent sets will be n choose k. So the inequality reads 1 is larger than 1 times 1. So this is very curious proof. It looks like we didn't do any hard work combinatorially. I mean, we didn't do any combinatorics. The only possible combinatorics that may come into play is checking the base case, the quadratic case, which is analysis of configuration in 2-dimensional spaces, which is kind of boring combinatorics. But it looks like that is the source of this kind of concavity, which is hard to justify by other means. So let me close by emphasizing that there is no algebraic geometry inspired or using proof of this fact, even for those realizable matroids where realization is in one of our favorite fields, something like C to the D. One can do some sort of a Hodge theory from the variety constructed from A in here, which is natural in all rights, but that only shows the weaker inequality, this. And of course, the proof of this also uses the same type of technique, which exploits the fact that the volume polynomial of a projective variety is Lorentzian. And you wiggle your H a little bit and improve this by something like k plus 1 over k. But this is like the absolute limit to my eyes that you can go with this method, unless you are deforming y. So in this Lorentzian polynomial, as you vary your H and explore your ample cone of your y constructed from this A, the polynomial travels around this space of Lorentzian polynomials, but you can never really go far enough unless you're willing to deform y, which doesn't really, I couldn't really make sense of it in this geometric setting. But just abstractly, you can just go all the way to the tight case if you go beyond the case of algebraic geometry. So the challenge for geometers is to come up with a nice geometric explanation for this inequality by finding a projective variety whose Hodge theory explains this enumerative consequence. So, okay, now I should tell you that I have said nothing about graph homomorphisms and cellularly embedded graphs and Cox-to-Matroids and representations of GLN and sure polynomials. Yeah, so you're clickbaited. So yeah. It's one thing I learned from YouTube. So I hope see you tomorrow. Yeah, thanks. Yeah.
Any questions?
Is there a connection of this to the total positivity of matrices?
If you give me totally positive matrix, I can produce one Lorentzian polynomial. But yeah,
Which is what?
take the basis generating polynomial of your totally positive D by N matrix, where the coefficient in front of the square-free monomial is the determinant of the corresponding square matrix. That is Lorentzian.
So if I have several totally positive matrices and I square totally positive matrices, I take determinant of mixed characteristic polynomial. So determinant of the sum of these matrices with coefficients Ti. Will this be Lorentzian?
So I cannot process in real time, but I hear lots of familiar keywords, and I would say that if you state it correctly, it will be true. That's my guess. Yeah.
Other questions? Okay, let's thank June again.
Yeah.